Now we have completed discussing the overview of the different aspects of superconductivity, and from now onwards we will be looking at certain more detailed aspects of superconductors. This will be the place where we will work out certain theories of superconductivity in more greater details to try and understand the phenomena of superconductivity. And we begin with the BCS theory of superconductors, where we will work out in details the gap, the zero temperature gap, how it arises, and what is the means, what is the details of that theory. That will be a set of lectures which we will follow. Now, before we work out the BCS theory of superconductors, the first thing that we will work out is the behavior of two electrons around the Fermi energy in the presence of very weak, arbitrarily weak attractive potential. If you take two electrons near the Fermi energy and you introduce an arbitrarily weak attractive potential in the system, how do these two electrons behave? Okay, that is the first starting off point of the BCS theory, and we will work out that aspect. This is pretty simple because it just requires Schrodinger's equations, and we will try and work out this problem. So now let us consider the two electrons which are sitting very close to the Fermi surface, whose energy is roughly, each electron has an energy which is roughly EF, which is the Fermi energy. Okay, and these two electrons experience an attractive potential V, which is R1 minus R2. Okay, so they experience an attractive potential V, which is R1 minus R2. Okay, and these two electrons are sitting very close to the Fermi energy. Now, if these two electrons were completely free, okay, then the energy of the two electron state, the total energy of this two electron state will be twice of EF, because each electron has an energy EF. Okay. Now, for the two electron system, one can write down the Schrodinger's equation, which is given here. Minus h cross square by 2m delta r1 square plus delta r2 square, where r1 and r2 are the position vectors of the individual electrons. The potential V r1 minus r2, and the wave function psi r1 r2, the two electron wave function psi r1 r2, which is equal to E psi r1 r2. Now notice that the potential R1 R2 does not depend on the spin of the electrons, and this will be our standard assumption in the present case, is that the potential through which the electrons interact with each other, these potential does not depend on the spin part. So in this wave function we are not considering the spin part. Okay, the spin part cancels out from this wave function. Okay, because the potential does not modify the spin part in any way. We just consider the spatial part of the wave function, and we will come back to this point later on, that it has some important consequences. Okay, now when you have this two electron Schrodinger's equation, which is written here, this two electron Schrodinger's wave equation is written here. Okay, this two particle Schrodinger's wave equation can be simplified by transforming to the relative coordinate and the center of mass coordinate. The relative coordinate is small r and the center of mass coordinate is capital R. Okay, and then you can show that you can transform this upper equation, Schrodinger's equation, to minus h cross square by 2 mu, where mu is the reduced mass, delta r square, r is the relative coordinate, minus h cross square by 2 m star, where m star is the total mass of the two electrons, which is 2m, delta capital R square plus V of r, this is the potential, and you are looking for solutions of psi which are functions of the relative coordinate and the center of mass coordinate. This relative coordinate and the center of mass coordinate is equal to E psi of r comma capital R, where capital R is the center of mass coordinate and small r is the relative coordinate. Okay, and mu is your reduced mass, which is m by 2, and m star is your total mass 2m of the system. Now V of r does not depend on your center of mass coordinate. So you are looking for solutions psi of r, you are looking for solutions psi of r, capital R, of the form psi of r e raised to I k dot r, okay, where the center of mass is just a plane wave solution e raised to I k of r. Okay, the potential does not do anything to the center of mass, so it leaves this part unmodified, is just a plane wave solution. And typically for BCS, k, which is the momentum of the center of mass, should be equal to 0. Here I would ask you to look back at my earlier discussion of BCS, where I have done a qualitative discussion of BCS theory. For BCS, for superconducting pairing, you actually prefer k is equal to center of mass momentum is equal to 0. So typically one will be looking at solutions of the form k is equal to 0, but in general we can define a total energy E. Okay, so if I put in this equation, so if I put in this, if I substitute this out here into my Schrodinger's equation, my general form will be of the Schrodinger's equation will be h cross square by 2 mu delta small r square plus V of r psi r is equal to E tilde psi r, where now you can see that you just depend on the relative coordinate. You just have this relative coordinate part which is now coming here, and E tilde is E minus h cross square capital K square by 2m star. E tilde is equal to this, and for BCS pairs, the center of mass momentum is equal to 0. Remember that this term h cross square k square by 2m star is basically coming from the above equation, from this term h cross square by 2m star delta r square, the delta r, where r is the center of mass momentum. It is from this expression that you are getting h cross square k square by 2m, which you take on the other side and you will get this form of the expression. So this is your k is your center of mass momentum, capital K is your center of mass momentum vector, and your E tilde is, in general, E tilde is related to E minus h cross square k square by 2m star. M star is the total mass, and for BCS k is equal to 0. For all practical purposes, for BCS pairs, the ground state has k is equal to 0, so it is equal to E. So if you want to look at the ground state, we will consider E star is equal to, or E tilde is equal to E. So by our basic equation will be minus h cross square by 2 mu delta r the whole square plus V of r psi r is equal to E psi r, where E is the ground state. This is for the ground state with center of mass momentum k is equal to 0. So now we define, to solve the above equation, the above Schrodinger's equation, if you want to solve this Schrodinger's equation, we actually first define, there are various ways of solving it. One of the ways is that we do a Fourier transform of the Schrodinger's equation. We take a Fourier transform of the Schrodinger's equation, which you see above here. Okay, written out in the relative coordinate. Okay, and for doing the Fourier transform, we define the Fourier transform of the wave function psi small k is equal to integral of psi r e raised to minus I k bar dot r bar dq bar, and psi r is equal to 1 by 2 pi cube d cube k psi r e raised to I k r. Okay, so we define this Fourier transform of the wave function, and then the above equation we can actually take its Fourier transform by integrating this expression minus h cross square by 2m delta r the whole square plus v of r psi of r e raised to minus I k bar dot r bar. We take the Fourier transform of this, we just multiply it by e raised to minus I k r and integrate it over dq bar over the entire volume of space, and similarly integral of e psi of r e raised to minus I k bar dot r bar dq bar. So we take the Fourier transform of the above Schrodinger's equation. This Schrodinger's equation which we have derived, we take the Fourier transform of it. Okay, now this type of thing you would have already done. Okay, you would have already done such type of Fourier transforms. Okay, so without getting into great details of it, I will just typically give you very brief working out of the Fourier transform. So first is the simplification of the first term, which is integral of minus h cross square, this is actually 2 mu, h cross square by 2 mu delta r the whole square psi of r e raised to minus I k bar dot r bar dq bar plus integral v of r psi of r e raised to minus I k bar dot r bar dq bar. This is equal to E integral psi of r e raised to minus I k bar dot r bar dq bar. Okay, so this is your, I am just opening out the brackets and taking the Fourier transform of each part of the equation. So in the above Fourier transform, let us consider the first term. Okay, the first term is minus h cross square by 2 mu integral of del square psi e raised to I minus I k bar dot r bar dq bar. This is nothing else but h cross square k square by 2 mu. For some it is obvious, this is just the direct Fourier transform which will give you h cross square k square by 2 mu, where k is the momentum vector. Okay, it is also easy to prove it. You will have to use integration by parts, and to see it, if I just write down this expression for the 1D case, if I write it down for 1D case, then this will be minus h cross square by 2 mu integral from minus infinity to plus infinity over the entire volume of space e raised to minus I kx d square psi by dx square dx. You use integration by parts, and if you use integration by parts, the above equation will be of this form. Okay, by doing integration by parts, and then you can simplify this to get these different expressions, and this term that you have here e raised to minus I kx d psi by dx, this itself can be once again integrated. Okay, and you will have this expression. Okay, ik e raised to minus ikx psi, this is after doing integration by parts, plus ik e raised to minus ikx d psi by dx. This you have to work it out yourself, it's quite trivial, or this entire thing, and then this is nothing else, this part is nothing else but the Fourier transform of psi x, which is psi k. Okay, this is nothing else but the Fourier transform of psi x, which is psi k. Okay, and the above these terms, these two terms, these other remaining terms actually become 0 in the limit of plus minus infinity, because the wave function has to be normalizable. So at infinity, these wave functions, the derivatives and their values actually go to 0. So at plus minus infinity they are 0. So these first two terms go to 0, and then your Fourier transform of that quantity e raised to ikx del square psi becomes h cos square k square by 2 mu psi k. Okay, so the first term of your and you can actually generalize it. Once you do it for 1D, you can easily generalize it for the xyz coordinates with kx, ky and kz, and you can show this expression very easily, also following the same procedure for the 3D case. Okay, so the first term of the expression equates to this. The second term also we will simplify it further, and the third term, which is this, is nothing else but psi k. Okay, so this above Fourier transform, let us simplify it further and let us write it down. Okay, so the first term of the Fourier transform is nothing else but h cross square k square by 2 mu psi k plus integral d cube q by 2 pi cube. I'll just first write down the expression. Okay, vq integral psi of r e raised to minus I k minus q dot r d cube r is equal to e. This is the Fourier transform of the simplified Schrodinger's equation that we had got, where all that I have done in the above expression is that v of r, I have written its Fourier transform, which is in terms of q d cube q by 2 pi cube. The volume in the momentum phase space d cube q v of q e raised to plus I q dot r. Following the convention which I have already described earlier for psi of r, we can write down v of r as integral d cube q integration over the momentum space 2 pi cube v q, this is vq e raised to iq, and then we just put it back in that expression, and that is how you get this term. So all that we have done is just do that. Okay, just replace this v of r in terms of the Fourier transform in this above expression. And now if q is k minus k prime, okay, if q is k minus k prime, then my above expression h cross square k square by 2 mu psi k plus integral d cube k prime by 2 pi cube v of k minus k prime integral psi of r e raised to plus I k prime dot r d cube r is equal to E psi k. Okay, where k and k prime are the momentas of the electrons. One has momentum k and another has momentum k prime. So this represents the two momentas of the particles. Q is k minus k prime. Okay, we are integrating over the momentum. Okay, now the potential is a function of the, here we can see that we are writing the potential in terms of the momentum. Okay, the potential is written in terms of the momentum, and this is how you get your expression. This is how you simplify your Schrodinger's equation, which you have Fourier transform for these two electrons which are interacting with this potential V. So now the Fourier transform of this Schrodinger's equation we had written down for this two particle system interacting by this potential V k k prime, which depends on the momentas k and k prime, is simplified to this form, which is written here. Okay, it is simplified to this form: integral d cube k 2 pi cube v k k prime. This is a potential which depends on k k prime. Okay, it's a potential k prime. Okay, k prime are the momentas of the two particles into psi k prime, the wave function in the momentum space, or the Fourier transform of the wave function, e minus h cross square k square by 2 mu, where I just have taken this term and taken it on this side, and this is nothing else but m by 2. So I can rewrite this as integral d cube k prime by 2 pi cube v k prime. I am just simplifying it and writing it like this: k prime is equal to e minus h cross square k square by m psi k. Okay, now if Ek is the energy of a free electron with momentum h cross k, then this is equal to h cross square k square by 2m. So twice of Ek is h cross square k square by m. So again, your above equation, I can rewrite it as d cube k prime by 2 pi cube v k prime psi k prime is equal to e minus 2 Ek psi k. Okay, so this equation is going to be the point from where we will make some important assumptions regarding the potential which is scattering k prime. Okay, the potential which is involved in scattering these electrons k prime with momentas k prime, we will make some important assumptions, which is the BCS form of the potential. Okay, BCS potential for k prime. We will make some assumptions, and that is what was given by the BCS theory. The BCS theory assumed some form of this potential which actually scatters this k prime electrons in the system, which are sitting just on the boundary of the Fermi energy. And that discussion we will continue it in the next lecture.